телевидении, Czech Technical University in Prague. Evgeny Shorokov, Moscow State University, Faculty of Physics. Oleg Katekin, University of Erlangen, Nuremberg, Germany. Sergio Palomares Ruiz, Institute of Corpuscular Physics, Paterna, Spain. And Federico Roskovich, Charles University of Prague. Last. Okay, so panel is formed. So we have some questions in some arbitrary sequence. So probably I would start with some simple question. Yes, coming with more complicated. So I propose to start with question number 2. As we have heard, this matter effects are almost proposed to be routinely used in the solving hierarchy problems. But the question is has been already proved experimentally that this matter effect do exist? And if yes, to what level? 3 sigma, 4 sigma, 5 sigma. So I propose to start with this discussion. So we start with if someone has, the panel has opinion. So who can say something about it? Is it working? If not, I can give you.
Yeah, I think it's working. Okay, simple question, simple answer would be yes. I think the matter effect was proved in the sun, and I think the reason for this question to be in a panel discussion is the recent result from Super-kamiokande. I'm looking into the paper, which says the result deviates by approximately 3%, and the certainty level is almost 3 sigma, 2.7 sigma. So that's a short answer from me.
Okay, thank you. More opinions on this subject?
So that 3%, actually there are two things in solar neutrinos. Actually, that is the only place where matter effects have showed up so far. And the 3% is a day-night effect, so it's an Earth effect, and that has been confirmed at the 3 sigma level at this moment. But we also have the matter effect at the sun, actually, that was discussed during some talk today. That is exactly what tells us what is the sign of the delta square 1, 2. And for that we need matter effects in the sun. So there are two places using solar neutrinos where we know matter effects are at place, which is the sun and the Earth. So I would say yes. It says yes.
Yes, you have both.
As he said, the matter effect is established by the solar neutrino measurement, but if the MSW is correct or not, we have to do more things for doing the detailed spectral measurement of the bromide neutrino packs. That's actually proves if the MSW is correct or not.
Okay, more opinions, probably in the auditorium. So, okay, then I think the conclusion is that we can expect the Nobel Prize in the coming years for observation of this effect, or prediction of this effect, yes, which is a pleasure to mention, and for observation. Yeah?
But for the
if you have no objections.
for the MSWs, as she said, I mean, one thing is the matter effect, and that I think we know, it's proven, and a different thing is the MSW effect. And the MSW effect, we will need to see the transition region with the solar neutrino spectrum. So far we have only data in the high energy side and in the low energy side. So we need the transition, and this we don't have data so far. With that, we'll have MSW effect proven.
Okay, thank you. I think now it's exhausted. Yeah. Okay, the next question is motivated by this new measurements of these elements of PMNS matrix, T213, T223, etc. So, how well do we need to know these matrix elements? I mean, it's already not bad measurement. Yes, including the last measurements of T213. So of course we should know about CP violation, but this real elements. Are there some motivations to measure further to better accuracy? So please, if you any order.
So, if I may start this, so I will start with the θ13 measurement, which we already saw that this is very important, like the large value and also the precision of that for delta CP measurement, because if we are lucky, we can measure delta CP if there will be some favorable value, but if there will be not, if it will be, I don't know, like close to 0 or something like that, the precision measurement of θ13 improve the coverage of delta CP phase space, like which can be explored by the accelerator experiments. So, and I would like to add that with the precision measurement of θ13 in Darby, I don't see in the future any other experiment which will achieve this kind of precision. So I think for Darby it is, and I mean for other people, for other studies, maybe for study physics beyond the standard model, I mean some non-standard interaction and whatever. It is important to have as good as, I would say, like the best precision of θ13 we can achieve. So this is one thing, and then I would add that there are some other experiments which can improve, I would say, very much the precision. For example, Juno experiment in China, which like the goal is to push the uncertainty of the mass square differences and solar angle θ12 below 1%. So we are getting like to the era of the precision measurement, and the measurement will be, the angles will be measured with more precisely than the CKM matrix.
Okay, so
So I think PMNS matrix, there are two goals for precision measurement. One is to determine all the parameters and constrain or give some hint on the origin of this PMNS matrix, like randomification theory. So that's for that purpose. Currently, delta CP is not known yet, so measuring that is important. And the next less precise one is θ23. So θ23 measurement is important. So that's the first goal. The second goal is like CKM matrix, like quark flavor physics. Over-constrain this matrix, and then look for physics beyond the standard, beyond this PMNS matrix is the next goal. And nice thing about neutrino spatial is that there's no long-range effect. So the core case, these long-range effects limit how well that one can measure these matrix. One can go for rate decay to further constraint, but it's still challenging. Whereas these neutrino case, it directly measure these parameters. And so the precision can go very, very well. And there are different approaches, different ways of measuring this. And so these new mutant, new E appearance, new mutant, new tau, or in the future, if the neutrino factory is built and new E to new tau, there are different ways of approaching this. And so that will allow us to over-constrain this matrix and look for further, like beyond this PMS matrix situation. So those are the two things that I think.
So if I understood correctly, you mean that we should check, say, unitarity, yes, of the matrix, and
Yes.
For that we need, say, similar accuracies for different terms to get good accuracy at the end.
Right.
So, okay. Are there more opinions from panel or from auditorium?
I can add something to that. So there is a couple of things I think it's also important to stress is that apart from all this precision, in the end you can always ask the question, so how far do you really want to go? We are at the few percent level, do we want to go at the percent level, do we want to go at the per mil level? What is the level we really want to reach? And that is a difficult question because some of these parameters are really model discriminators. And there is another parameter, so maybe 1% is enough to discriminate a lot of models. There are some models within below the percent level. So that is an important question if we really want to search for some greater theory that embeds neutrino masses and so on. And there is another parameter that hasn't been mentioned now, which is the neutrino mass hierarchy that we have discussed during the talks. And that is really a big model discriminator. And not only that, not only is a big model discriminator, along with also theta 2-3 that we only know, so far we only know sine squared 2 theta 2-3, so we don't know the octant. But the mass hierarchy is also very important for neutrinos double beta decay, which is one of the crucial things in neutrino physics, which is knowing what is the nature of neutrinos, if we have Majorana or Dirac neutrinos. And measuring the mass hierarchy would also help a lot in discriminating, in telling us if a future measurement of neutrinos double beta decay, either positive or null, will tell us if neutrinos are Majorana particles, and this is a crucial question too. These are two things I want to stress.
Okay, thank you. So,
Maybe I can add. It mostly relates to the comments before me. I think efficiency of measurement of neutrino mass hierarchy also depends on the precision of theta 2-3 parameter, and if to moment of measurement of mass hierarchy we will know this parameter more precise, then we can quickly discriminate between two possible mass hierarchies.
okay, there is question number 5 that kind of relate to the discussion. What are the main other important problems in neutrino physics? Say, CP violation, mass hierarchy, which was already mentioned. What else?
So we already mentioned CP violation mass hierarchy. Then it was already mentioned the octant of theta 2-3. Then the origin of the neutrino mass. So that means if they are pure Dirac or they are Majorana. And also these measurements can be measured basically in the oscillation experiments, but they are. The Majorana can be measured basically in neutrino double beta decay. And I would add one more, and I think this is the absolute neutrino mass, which there is this Katrina experiment, which we probably already everybody heard about that, but there are still no results. So it reminds me like alpha experiment within Atlas, because everybody heard about it, but there are basically no results. So hopefully Katrina will be working, and we will hopefully see some results and have an absolute neutrino mass.
Okay. Other opinions? So basically, we focused on this known questions. Okay.
In my opinion, but it relates to another question if sterile neutrino
Yeah,
exists.
it's
Yeah,
aside. Yes,
Okay.
then we turn to, because one of the remaining yes, and perhaps it is kind of great problems, is the problem of if sterile neutrinos exist. Yes, so it's some subject for separate discussion. And so here we heard already quite some results. Diabetes, for example, etc. So this reactor anomaly. So then I would like to propose you to discuss other possibilities. Yes, because not everything was presented during session. For example, this source experiments with source, etc., etc. So if you can say what are good directions in studying this problem, in attacking this problem, please tell us. Yeah?
Actually, there is one question which is missing, I feel. Maybe I misunderstood something. What is the force causing the neutrino oscillations? That is a question it's a completely principal question, of course, but it's a fact that you need one more force in order to oscillate the neutrino.
If you have some opinions.
So this is, I'm not sure that I understand the question well, but just mass against state and flavor against state.
Yes. What causes the difference between them?
Oh, the structure.
Yes.
Oh, so I think that one is a question that probably going to a granularification theory or something that is behind it. This is a mass matrix, and so what is the mechanism of that creates the neutrino mass? It goes to there, and it looks like it's not like just a Higgs mechanism. So something is behind it, and we don't know, and so we need to get more information and then try to get guess or develop the idea of where it is coming from.
So it's more or less the equivalent to the question of origin of the mass of the neutrinos. Yes.
Yeah. I'm sorry I have to dispute with that, because the fermion masses we just impose on the standard model. We can do the same with the neutrinos as well, no problem. You just add those terms to the Lagrangian. The oscillation is the one which, as I feel, causes the problem.
Very small scale for neutrinos.
Yes, okay, that's good. Yes.
Unusual.
Yeah.
I just have a really tiny comment about the force. I wouldn't go that far, because 100 years ago there was something unknown. Physicists invented a new kind of force which is causing it. But as we said before, all those topics or questions are closely connected. I would maybe connect this one with the sterile neutrino, which might cause the oscillations. But also then there is the other question, what is the cause and what is the effect? Is the oscillation a cause or the effect of having the mass?
Okay, so if I may add and react to your question, so I would say that the first step to like investigate the origin of neutrino mass is to investigate if they are Mariana or Dirac. So we've got some theories which can generate this Mariana mass term, and either we need sterile neutrinos or double charged Higgs or whatever. So I think the important is, like, from the experimental point of view, the first step is to measure the double beta decay and say, okay, they are Mariana, and we can go on with these theories. If we measure, if we, for example, find out that there is an inverted hierarchy and we get below some point that we can say they are purely Dirac, then all of these seesaw mechanisms and so on, we can reject them and then we have to try to look somewhere else. But from theoretical point of view, okay, yeah, let's suggest a lot of theories, but experimenters should measure the neutrino by better decay.
Okay. So one of the popular explanation is that this heavy right-handed neutrino at the granularification theory level would, for example, SO10 naturally would get that into it, and then that will explain the seesaw mechanism to produce the light neutrino, and that mechanism could produce this, and each coupling of these right-handed neutrino could produce this MNS matrix, which also couples with the Dirac coupling as well, and so these two are mixed together, and then so more democratic type mixing matrix may be there. So that's one a very convincing conjecture that I hear from theorists. So there are possibilities at this point, but until more data and information is there and then understanding is there, it's hard to tell.
I may comment this. So this as you told, like this heavy right-handed sterile neutrino, this theory is called like seesaw type 1, that we've got this right-handed neutrino, but its mass is about like 10 to the 50. It's really heavy, and probably we won't be able to observe that. And there are some other seesaw mechanisms where we do not need the right-handed neutrino, and there won't be any sterile neutrinos. So just a comment that I mean, in order to explain like the light mass, like relatively light mass compared to the other particles, we do not need right-handed so-called sterile neutrino.
One more small information. There's a nice white paper about the light sterile neutrino from April of 2012. It's in archives, so if you look it up, you can read all the type mechanisms and all possibilities for right-handed neutrinos.
So, about then returning again to sterile neutrinos. So, this let's say rather different type of experiments which are now being proposed. Say this proposal that's ship experiment, which is beam damp, and after you look for vertices. Yes. So it's like PS 191 old certain experiment where rather than leave it for sterile neutrino or it's forward. So we didn't hear about it, yes, at all. And then this source experiments, which were also not covered. So what is your opinion about the perspective of these specific directions, which are kind of special?
So I don't know much about these experiments, but what we learned from the past that like these experiments like LSND or Mini-Boon, they've got always a problem with the prediction of their background, and they reported some sterile neutrinos which were then disapproved. So I would say to have this, for example, the ship experiment is, I mean, if we want to find a right-handed or sterile neutrino, then we need much more energy than it will be possible to get from this beam dump. So I'm not really a fan of these experiments at all, and I know a little bit about chip, and I think the energy is not enough, and building this experiment just only for the purpose that we know that we will find nothing, then I don't think it is worth for that.
So your concern is that the region which they cover is too short, yes?
Yeah. I mean,
Mass.
I mean, basically nobody is expecting to find anything in this region. Like, I don't know any theory which will predict something about in TV region. So.
Formally, they refer to this paper of Abushinka and others. There was another collaborator. So where this famous allowed region derived from astrophysical concepts is put forward. And then one of the approaches is that you start your experimentals, you should cover all this region. Yes. So SHIP certainly covers a fraction of it, but not.
Yeah,
not
of course, like for covering some region, okay, it is okay. But for me, like the most promising, more promising way how to find it is to look for some loop corrections of this particle on like existing accelerators. I think it does not work for building a new experiment.
I just learned about ship experiment by looking at the webpage today, but my impression is that it is more related to a dark matter search. So dark sector is there, and then decay of that dark particle. So like a dark photon like experiment, there is a beam dump, and then after that some new particle comes, and that can be a heavy neutrino as well, of course. That's a good candidate for dark matter. And there, like at this point, we don't know where dark matter is, and it can be a very light to a very, very heavy region. So wherever we can find it, look for it is worth doing, I think. And in a sense that neutrino is like dark matter as well. It is produced in the beam dump, and then or decay pipe, and then go through and then travel through the beam dump, and then you can detect it somewhere. So this is one way, good way for using accelerator to search for such a potential dark matter candidate. So just if there is a tool there to do it, then I think it's worth doing, because dark matter is so important.
Yeah, you have already commented part of what I wanted to say, but the real crucial thing here is the cost. Because if we are all physicists, so if you give us a couple of billions of dollars, we built a huge accelerator and I don't know, detector on the moon, and then we are fine. But I like the idea of using the existing beam, and maybe I would think. Talking about chip, I would think about, I don't know, filling the tube with helium instead of sustaining the high vacuum, because the effect would be negligible. I think it would be much more cheaper. But talking about those new experiments, it's a specific thing about the neutrino physics is it's rather scattered among all the, I don't know, governments or all the world. And if we want to build something like really big and multi-purpose, you have to work forward to get all things in common sense and think in a global scale. A recent paper from Snowmass, I think, was talking just about US physics. I'm talking here from Fremont now. But I think we should follow what the European countries do and try to add everything up and think globally, like building different accelerators or different sources of neutrinos and maybe some huge detector, like I don't know, which costs money. That's again the problem.
So can I add something on these lines? So I'll be a little bit provocative. So I will disagree with the first two comments. So I think these kind of experiments are important, and it's not true that they don't cover important ranges in the parameter space. They do cover a lot of the parameter space, which is important. You might think that a GeV heavy stellar neutrino is not important, but because it does nothing. It does nothing in a small picture. It does a lot in the whole picture. As you mentioned, the moderator mentioned, there is this Shabashnikov model where there is this new standard model, which is just 3 right-handed neutrinos. And in that model, they claim they can have a dark matter candidate. They can explain baryogenesis. They can explain some other even inflation with some additions. And in those models, you need, for example, GeV heavy stellar neutrinos. So this, for example, shape experiment will have access to neutrino masses. I mean, right-handed neutrinos with masses below, say, 1, 2 GeV. So, and that is right range, which is predicted within this class of models, that we would have to see some neutrino that within the whole picture will be accompanied by a dark matter candidate, for example, and could explain neutrino masses. So I think this is interesting to pursue. I don't know the details of SHIP. I don't know how far they will get in the parameter space, but I think it's definitely worth pursuing neutrino masses below 3 GeV. And actually, I think those are even more interesting from the point of view of model building than searching electron ball stellar neutrino. Electron ball stellar neutrino doesn't usually fit in any model. So actually, in principle, from a model building point of view, it's more interesting to search for GeV, MEV neutrinos that might not do anything in the small picture, but a lot in the whole picture. And then there was mention of this shape that could be also detecting the dark matter. I actually disagree with that. SHIP cannot detect the dark matter because the concept of SHIP is you have charm mesons decaying into neutrinos, and those neutrinos would mix with this heavy stellar neutrino, and that heavy stellar neutrino would decay. So that heavy stellar neutrino cannot be the dark matter because otherwise it would decay. So this is the way this heavy stellar neutrino is detected in SHIP. It has a drawback because this is penalized by the fourth power of the mixing angle because you need to produce and then decay. But this is part of the game. But it cannot be the dark matter. That neutrino would be embedded in a bigger picture, as I said before, that could include dark matter, but the detected one will not be the dark matter. And I would like also to mention a few things about, just a comment on this stellar neutrino thing. Stellar neutrinos appear in many places. I mean, they can be important if they have electron ball masses. It could be affecting a lot. For example, the evolution of the universe, affecting the extra degrees of freedom in the early universe, and actually it could be a good explanation for the Euler excess, like experiments like WMAP have seen. In KV ranges, they could be very good dark matter candidates. Actually, we have now a hint of a gamma ray signal that could be produced by a neutrino decay, dark matter neutrino decay with lifetimes longer than the age of the universe, and we have a hint of this signal with 3.5 keV. So that could be explained if confirmed by stellar neutrinos. Again, stellar neutrinos could be higher in mass and could be part of the mass mechanism of CISO or higher scales. Any neutrino different with any mass could be part of the mass mechanism. It could be 10 to the 14, but you can have a TeV neutrino and explain neutrino masses. And those TeV neutrinos, for example, could show up in lepton flavor violation experiments and in LHC. So stellar neutrinos, heavy right-handed neutrinos, appear in many places in physics. and it's actually worth to see, to search for those, because we don't know what the mass mechanism is, and it could show up at any mass and in any place. So, and they have effects in many different fields of physics and astrophysics and cosmology.
Okay, thank you. So, but then another type of experiment. So, so what to do with LSND, mini boon, etc. All these elements. So there is a proposal. Carl is proposing to put Icarus, say 1 kilometer from the target, and to look directly for electron neutrinos with L over E in the region of 1. Yes, he is proposing. Has been proposing to put Icarus at CERN, but the proposal is rejected. Yes, then he is proposing to put it into terminal. So if somebody knows about events happening, is it approved or to be approved? He even has proposed to put Neutrino here because we have a relatively good neutrino beam with a very low mixture of electron neutrinos, is below 0.5%, and energy is say 1-2 J, and we can put Icarus actually not far from this place, one kilometer from here, and we are there. So, what is your opinion about this type of experiments, specifically for Icarus?
Well, well, Icarus, I actually don't know what is the current situation of this. Is definitely to improve. For example, the proposal to move to CERN will definitely improve because it's a new detector that is very important for these searches at this moment. But there are other proposals. There is another proposal in the US. I never remember the name, something like SNS oscillations or something like that. They claim they would improve it's similar to LSND experiment, and they would improve like an order of magnitude in mixing. And there is also, there was, I think, no storm, which was another proposal using a low energy neutrino factory. I think this was not approved by the P5. And well, definitely the microboon could also do that. So I think it is worth, as I said, CERN neutrinos could show up anywhere, and it is worth it.
Okay, other opinions?
So, so the proposal is Icarus is presented to terminal PSC. There are other liquid argon projects, like like a smaller liquid argon detector, like microboon detector. So it looks like the direction that it is going is to have 2 or 3 detectors. So Icarus is the biggest one, farthest away, but having different detector at different location. So I think this LSND result or minimum result, the challenge is that just one parameter, trying to get one parameter and then try to extract the information. So whenever you have some kind of systematic error, in this case, the challenge is to understand the nuclear effect. So neutrino interaction with the nuclear effect, and that's very, very complicated. Minimum has shown that CCQE, quasi-elastic cross-section, is 20-30% off, and still we don't know how to explain it. Like there are sort of model is there, but not complete. And still a lot of discussion is going. So under such a situation, redundancy or over-constraining configuration is very important. So maybe these are 3 or even more detector at the different baseline length is one possibility.
Okay. More opinions? Okay, so yes, that's question.
Why not the experiment measure the absolute value of neutrinos from beta decay, for example? The oscillation has proved the square mass difference also, and the mixing angle also. And the next is the CD phase.
So you are speaking about direct measurement of the mass of neutrino mass, yes? Not delta m squared, but direct measurement. Yes. But Okay, there is, there are,
sensitivity.
yeah, it's, probably is.
Yeah,
It's
I
around
think-
1 electron volt, yes, is now.
Now the upper limit
the limit is 1 electron volt.
Because we can build a model to explain some seesaw mechanism, how about the neutrino mass, like standard model or SUSI or something like that. So
But there is,
problem is,
but there is a,
what's
there is,
the limit of the lower limit of neutrino mass?
yeah, but
only
there,
the
there
upper
is a running project in Germany, yes.
Yeah, so you're proposing to measure direct measurement
Yeah.
through beta decay
It's more
of the
important.
absolute mass, and that's exactly what Kepler does.
Catherine, exactly.
Times higher than astrophysical prediction of Neutrino mass.
So probably this last astrophysical question, yeah, no, is if someone has opinion on that, this several time analysis of the long time neutrino observations give information about the galaxy distribution and the local universe. But if so, if
I
there are,
can comment.
yeah,
I think this originates from gravitational wave detector experiment, because there is such paper explaining this method. And this method is really for particular detector with very bad angular resolution, and for particular constellation of sources of gravitational wave, then one or only two sources. And that's, in this case, this expected counting rate of such events, such gravitational waves, will have some minimum when detector is turned to this source with a not very sensitive part, let's say. But if you have many sources, then this picture will be smeared out. And then I think this method is not really relevant to neutrino astronomy. If you have real good resolution of original direction of neutrino, you simply, of course, use calculation of position on the sky through this serial time. But all this method go further than that serial analysis. And simply people put position of neutrino on the sky and look if it is a random position or there are some clusters which can indicate some sources of neutrino.
okay, more opinions, please.
There was such an experiment, but I completely agree. It was studying, I think it was Baba, we studied the Lorentz, possible Lorentz violation using this method. But it was not related to neutrinos or something. It's just the relative position of the experiment was checked somewhere in region.
Okay,
So, may I comment
Yeah.
this? I mean, you comment that they studied Lorentz violation, but it does not, think something about the local universe distribution, the galaxy or whatever. But you said that Baba, but there is a paper from Double-Show Corporation that they study this violation of Lorentz invariation using neutrinos, and also there is a proposal to study it at their base. So I'm not referring to this like galaxy distribution, but the Lorentz invariance was studied at Double-Show experiment and will be studied at their way to this possible Lorentz invariation.
okay, I think organizers are pushing that we should stop the discussion because otherwise the program will be broken. So let us thank panelists for very useful discussion. Thank you very much.